In this video, we will present the algorithm of steepest descent. As with almost all the algorithms that we've seen. In this video, we will present the algorithm called steepest descent. As with all the algorithms we have seen, we have an objective function, in this case called f, and represented in this figure here, where we're trying to find for what coordinates do we have the minimum or the maximum of the function, or the optimum. In this example, we will talk only about the minimum of the function. In order to make the case a bit more visual, besides the 3D plot of the function, we will also use the contour of the function, which is presented here on the right. If you don't remember how to read the contour or what it represents, please check the relevant video. As with all the algorithms that we have seen, our search for an optimum of the function starts with an initial guess. In this case, the initial guess is represented here with this red point, and we can see it both on the contour and on the 3D plot. This initial guess, as always, can be either informed based on prior knowledge, or it can be random. Another notion that we need in order to use this algorithm is the notion of the gradient. As you might remember, the gradient is evaluated at each point, and it is represented by a vector evaluated at each point. For a function with two variables, the gradient is a vector of two elements, or two coordinates. We are representing the gradient of this function in the contour, evaluated at different points along the function. If you don't remember how to read the gradient, please check the relevant video. Now, if we zoom in closer on the point that we have used as our initial guess, we will see that the vector of the gradient has a certain direction. We are using this direction in order to perform a more informed search for our optimum. Now, what direction does the vector of the gradient show me? As you can see in this example, the direction of the gradient points to the left, and towards the left from this point is where the function grows the steepest. So I can use this direction in order to perform a more informed search for my optimum. We can draw this direction both on the contour and on the surface plot of the function. Now, since, as I mentioned in the beginning, we are trying to find the minimum of the function, it doesn't make sense to look for the minimum in the direction where the function grows the fastest, rather than in the direction where it drops the fastest, or in the direction of the steepest descent. Therefore, starting from the direction that the gradient gives me, which is the direction where the function grows the fastest, I move along the opposite direction. So starting from the initial point, I calculate the gradient and I start moving on the opposite direction. How do I calculate this direction? I calculate it by starting from the initial point and using the gradient. The gradient is a vector which length is depending on how steep the function is. For a very steep slope of the function, the gradient will be a very big vector, where if the function is rather flat, the vector will be a small vector. In order to make the algorithm a bit more robust, we need to normalize this vector and make it be of unit length 1. We do this by dividing by the norm of the vector, which is a scalar. And by dividing the gradient evaluated at one point with the length or the norm of the vector, I end up having a unit length vector pointing along the same direction. To define the line that passes from this point and follows the same direction as the gradient, I define an extra variable and I subtract the multiplication of the variable with the unit length vector. I subtract it from the initial point. This results in another vector. By plugging this vector in my initial function f, I end up with another function which only depends on variable s. This makes it a function of one variable. How does that function look like? You can imagine a function that follows this line here as it's cutting along the function f. We can visualize this on the figure here below. This is the function that we have constructed here by using the initial guess, the direction of the gradient and a variable s, in order to define a function with one variable running along this direction, passing from this point on top of our initial function f. Now, since this is a one variable function, I can perform a search on this function in order to find the minimum using one of the algorithms that we have seen, namely the Fibonacci Oligonder ratio. By performing a search using the elimination method, I calculate a certain distance of where the minimum is along this function. This distance we call the step, and it is the solution of this minimization of this function. Now we can see that this step represents a new point along my original function. How do I calculate this new point? I calculate it using almost the same formula that I used to construct the function. I start with my initial point minus the step that I have calculated times the direction given by the gradient. And by this I calculate a new point. The function evaluated to this new point has a lower value, so we're closer to a new minimum. Now we can use this new point as a new starting point and repeat the process. So this part of the algorithm keeps on repeating and repeating. We define the gradient at that point, we figure out what is the direction, and we move along the negative direction of the gradient. We define our one variable function along that direction, and we perform the search. When we find the step size, we use it in order to calculate our new point. You can see how the point progressively goes closer and closer to one of the local minima. And we keep on repeating this part of the algorithm. Until when do we keep on repeating this? We keep on repeating it until one of the stopping criteria is satisfied. We have seen already that there are several different types of stopping criteria. We can use any of the ones that we have seen so far. It can be either that two consecutive points are very close to each other, or that the norm of the gradient is very, very close to zero. If we keep on repeating this method, here I start with a new point, I define the gradient, I take the direction, and I write my new function, and I perform the line search. We see that after a few iterations, I will end up close to a local minimum. This is how the steepest descent algorithm is working.